All right, this video is going to focus on the ideas of projectile motion and a little bit of review on some free fall ideas as well. For AP Physics, this would correspond to the Chapter 3 problems. For regular physics, this will be when we're doing our projectile problems. Okay? So let's go ahead and reintroduce the idea of free fall. So when something is in free fall, we are saying that the only thing that is acting on it, or the only thing we're considering to act on it, is the force of gravity. So we're neglecting things like air resistance. And a slight look ahead, eventually we're going to learn about free body diagrams, and our simplest free body diagram will be when things are in free fall. The only thing pulling on the object will be that force of gravity, or if you wanted to call it force of weight, eventually when you abbreviate, probably one of those two. So we got gravity pulling down on it. Okay, I'm going to go ahead and erase that one. Okay, and if there's only one thing acting on it, then our acceleration will be due entirely to that thing. So when we're in free fall, we can assume that the acceleration in the y direction is going to have a magnitude of 9.8 meters per second squared, as long as we're near the surface of the Earth. And if we are calling up positive, we can go ahead and put a negative on that if we're substituting in our numbers. Okay? So if I'm calling up positive, that's going to be my acceleration in the y direction for all my free fall problems. And we've had some of those before where it was just dropping something or tossing something straight up. Now what we're going to do is talk about projectile problems, or 2D motion, with our free fall ideas. Okay? So the idea is we basically have something like this. Something flying through the air like that, okay? And it could be thrown like that, it could be thrown like that, okay? It could be thrown sideways initially. And in all those cases, we're going to have a parabola that opens downward, okay? So we're going to be talking about it being a parabola at some point, okay? Later on, that'll pop up occasionally, okay? And how are we going to deal with these problems, okay? Well, the first thing that you want to do is you want to try to separate out the x from the y direction. If this was a normal year in class, I would have rolled Mario Ball and dropped Mario Ball from the desk in the back of the room type of deal. This year for AP, you watched the physics girl talk about this. For physics, I've either talked about it in class or I'm going to talk about it right now. If you fire a bullet horizontally, and as it leaves the barrel, you drop another bullet. Or in the classroom, if I had Mario Ball rolling along a flat desk, as he leaves the desk, another Mario Ball is dropped. So I got this one rolling along real fast, and as it leaves the surface, another Mario Ball is dropped from the same height. When do they hit the ground? Does this one hit first, the Mario Ball that is moving horizontally, or the bullet that's fired horizontally? Does the one that's dropped, forget the string, it doesn't matter. Does the one that's dropped hit first, or do they hit at the same time? So what do you think? And this might be a review for some of you, or new for others. Well, they both hit at the same time. Okay, now the question is why? Go ahead and get this up here. So there's the path of one of them. Make that a little bit more. There we go. There's the path of one of them. And the path of the other one will just be, those drop from here, will just be like that type of deal. So we got that versus that. Well, if we look at just the y direction, and that's one of the big things here, is separate the x from the y. If we look at just the y direction, this, if it was fired horizontally, it was dropped in the y direction. Its initial velocity in the y direction was 0. This one was dropped in the y direction. They both have the same acceleration, and they both have the same displacement in the y direction. So they have three variables that are the same. That means the time it takes to hit the ground when you use the motion equations will also have to be the same. Also, their final velocity in the y direction would also be the same. All right? So this is that idea that we're going to separate the x from the y direction, because we just look at the y direction to figure out when they're going to hit the ground, and then separately we can figure out what's happening at the x direction. Okay? So visually, what you should be doing in your brain for all of our projectile problems is, since there's no forces in the x direction, there's no acceleration in the x direction. In fact, I can write that up here as well. For all of our projectile problems, acceleration in the x, 0 meters per second squared. What does that mean? Okay? That means if you're picturing the object being launched to the right, okay, that means in all of our problems, you can picture Mario Ball or whatever the object is just steadily moving to the right. That's it. They're all going to be steadily moving to the right. In the y direction, what's going to be happening? Well, if it was launched like this, the y component would be up. It's tossed upward. So you can picture that's happening in the y direction. Or it's being dropped in the y direction, or it's being thrown down in the y direction. And we've done some problems like that already, and they haven't changed. So it's basically, as long as you can separate out the x from the y direction, you've done these problems before. It's just a matter of dealing with them all at the same time. And in the x direction, things are pretty simple because there's no acceleration. It's just an object steadily moving one way the whole time. It's just a matter of putting them together. Okay? And then obviously, occasional slightly tougher problems than that where you're mixing in other ideas as well. Okay? But for a basic projectile problem, that's all that's going on. So that's the key. That's the key. Picture Mario ball moving steadily to the right, and then separately what's happening in the y direction. So when we're listing our 5 variables, that's what you need to do. Okay? So for the y direction, y minus y naught, acceleration in the y, initial velocity in the y, v final in the y, and time. You should be using y's on here, and you have to be using a y right here, that y minus y naught, for these two-dimensional problems. Okay? For the x direction, let's talk a little bit about that. Well, our acceleration is 0. So if you go ahead, get your motion equations out right now. We're going to look at the first 3. Okay? And the first one is something like that, right? Well, if our acceleration in the x direction is 0, this whole thing is 0, and this tells us that our v final in the x is equal to our v initial in the x. We already knew that. It's not accelerating. The velocity in the x direction stays the same, okay? So that's just like 5 equals 5. While true, not very useful, okay? The second one, that's not the second one you guys have. This might be the second or the third one, okay? I think this might be the third one. V final squared equals v naught squared plus 2a. I'll use the x's, throw the x's on there. Acceleration is 0. Again, this turns into 0. This tells us something we already know. Okay? The other one is useful. X minus x naught equals v naught x, v naught t plus 1/2 at squared. Our acceleration is 0, so 0 times all of this stuff will just give us 0. And we're left with the one equation that we really need when our acceleration is 0. And that is that displacement equals velocity times time. In terms of speeds and distances, you're already familiar with this idea. If I said you were going 50 miles per hour in your car, 50 miles per hour, 50 miles per hour, and you traveled for 2 hours, and I asked you how far you went, you'd take the 50, you'd multiply by the 2, and you'd get 100. Slap on a direction here and a direction here, and now you've got displacement. Okay? So 50 miles per hour north, 50 miles per hour north, 50 miles per hour north for 2 hours, you're going 100 miles per hour, 100 miles to the north. And the fourth and the fifth will turn into something similar as well. And remember, v initial is the same thing as v final because we're not accelerating. Our velocity in the x stays the same. So typically what I do is I don't list my 5 variables when I have accelerations that are 0. It's overkill. You don't need to do all of this for the x direction on a projectile problem. Once you identify that the acceleration is 0 for any problem in a direction, all you really need in terms of motion equations is this. Now, I didn't write v initial or v final there because it's sufficient to just write vx because the velocity in the x direction stays the same. So that's enough. You don't have to, if you write v naught x or v final x, that's fine, as long as you know that that velocity in the x is the same through the entire problem. Okay? So this is the only equation we need for the x direction. For the y direction, you still need all the motion equations. Okay? For the x, that's all you need. For the y, you still need all of them. All right, so let's go ahead and start a problem so you can see how to deal with the beginning of the problem as well. And let me go ahead and I'm just going to make this smaller when we do the problem. So that'll come back here in a minute. And now we're actually doing a start of a projectile problem. If you want to see me finish a projectile problem, and there might even be one assigned at some point, I have other videos on YouTube where I do complete projectile problems. Okay, so I'm going to say some words here that will count as the problem. Let's say Mario ball is launched at 30 degrees above the horizontal at 8 meters per second. So 30 degrees above the horizontal at 8 meters per second. Mario ball is launched, so he's going to do something like this from a 12-meter cliff. There are lots of questions that I could ask you guys. I could say, how long is he in the air? Time to the highest point. How far does he land from the base of the cliff? And you will get practice with some, if not all of those at some point. Okay? All right. But for this one, let's just pretend like I'm looking for hang time. which is a fancy way of saying total time. Well, not a fancy. It's one way of saying total time in the air. Okay, so we're looking for total time in the air. So what do I do? Okay, well, the first thing, oh, and let's also say I'm looking for how far he lands from the base of the cliff. How far from the cliff? So I'm looking for this right here, x minus x naught, that displacement in the x, and I'm also looking for my total time in the air. All right, so what would I do to start this problem? Well, right away, you got to deal with the 8 meters per second and the 30 degrees. Components. Right? So my v naught in the x would be 8 meters per second cosine 30. So for AP, you're doing your SOHCAHTOA stuff. For physics, you've got your choice on how to get your components there. My v naught y would be 8 meters per second sine of 30 degrees. So you get those two numbers. So you go ahead and get those two numbers, break it into its components. Now I'm going to change something here to help emphasize an idea. When I'm doing a problem where I know it is a projectile problem and that my acceleration in the x will be 0 because I'm in free fall the whole time, the only thing affecting it is gravity, I'll go ahead and just write vx. Okay? It's not wrong to put v naught x. This is me just emphasizing that this velocity in the x direction stays the same. It's like a reminder to the class or to myself that this is going to stay the same when I use that notation. Okay? Whereas my velocity in the y is absolutely going to change because gravity, right? This thing is going to be fired up. Okay? It's going to go up off the cliff, and then it's going to start to come back down again, keep going, and hit the ground down below. So that velocity in the y direction is changing magnitude and direction, because sometimes it's going up, sometimes it's going down. Okay? So that's what you would do there. And now you would decide which one of these you want to attack first. Well, let's say that I wanted to try to figure out how far he was going from the base of the cliff. That's the displacement in the x direction. I've only got one equation, so I would write it. X minus x naught equals vxt. And I'd be like, okay, I got this number. I can figure that out, but I don't have time. Okay, so it's what is the time that it's in the air, because we need that to be able to find displacement. And time is the one thing of our 5 variables that is a scalar, meaning it only has magnitude. It doesn't make sense to say time in the x direction versus time in the y direction, right? That doesn't, it's just time, right? It's the time the object was in the air in this case. And that time then is shared. It's the one variable that's the same in the x and the y because it's a scalar. It doesn't care about direction. All the other ones you got to treat separately. So to find time, I can go, if I'm stuck with that, I can go look at the y direction. Okay, so let's go ahead and do that. So I'm going to go ahead now and list my 5 variables for the y direction. Y minus y naught, acceleration in the y, initial velocity in the y, final velocity in the y, and time. And I want to try to fill out 3, just like we were doing before on other problems. Okay, and if you can do that, you're home free. And if it's not something you can fill out, especially for AP problems or really tough physics problems, if it's something you know you'll be able to find with some other equation, put a check by it. Be like, I want that in my equation. But in this case, we would have the numbers. So our displacement in the y, we started here, we finished down here. Yes, we went up first, but then we came back down. It's a displacement of 0, and then we went down 12 more. Or where did you start in the vertical direction? Remember, we're trying to keep these separate in our brain. In the vertical direction, where did you start? In the vertical or the y direction, where did you finish? On the ground. So that's down 12. So down 12. So negative 12 meters. Assuming we're calling up, positive. I'm also going to put that there. We do need to define which way is positive on these problems. You got to have a picture and which way is positive when you're doing one of these problems on your paper. Okay? Otherwise, your work doesn't really mean anything. So you got to do that. You got to do that. Which way is positive and a picture. Because maybe you pictured this going to the left, right? Well, and then maybe you pictured left positive. That's important. I need to know that. Okay, I can't read your minds. Okay, so displacement's negative 12. Acceleration, because this is a projectile problem and we're assuming free fall. In other words, neglecting things like air resistance. Our acceleration in the y direction, negative 9.8 meters per second squared. Our initial velocity in the y, I can get that number if I want to. I can grab a calculator, make sure you're in degree mode. Don't forget to be in degree mode, but I can get that number. So now, there's 2 things we don't know, but we know 3 of them. So we can now solve for time. So you pick an equation, solve for time. Once you have that time, now you can go over here and solve for displacement. That's the overview of how to start one of these problems. Okay, so picture, which way is positive. Okay, get your components if it's at an angle. If it's at an angle, get your components. And then in your brain, picture what's happening in the x and y direction separately. So in the x direction, Mario ball, just steadily moving to the right. In the y direction, he's going up and then coming back down to land at the base of the cliff, 12 meters below where he started. Okay. Let's see here, a couple other things about free fall problems. If it's launched horizontally, you fire something horizontally. We kind of already talked about this, but it's being dropped in the y direction, because is there a y component if our vector looks like this? No, the y component's 0, right? It's all in the x direction. So that's a case if something's fired horizontally where the initial velocity in the y would be 0, and you wouldn't have to do this, right? It would just be initial velocity in the y 0, velocity in the x, whatever they told you, if fired horizontally. If something's fired vertically, like straight up or straight down, well, now it's not really a 2D projectile problem, right? It's just something being tossed up or thrown down. It's just the y part ideas without the components, okay? And we've done those before. That's it. All right.